So this is how you can calculate the CFSE of the complex. That is, CFSE can be calculated based on the nature of the ligand mainly. For example, if at all they had given ruthenium complex, that is this complex, if at all they are giving, right, 4 plus they had given. Ruthenium complex, same, for example, we will be having the complexes of manganese, Mn, water 6 times 2 plus. This is what kind of complex it is? It's both are octahedral complex. Remember, this complex is a high spin complex. Why it is a high spin complex? Because delta naught, it is high spin complex. Try understanding, it's high spin complex because this is delta naught is lesser than the pairing energy. Delta naught is very small, but it is a low spin complex, student. It's a low spin complex. Why? Because I already said when the metal ion comes into the picture, 4D and 5D doesn't need the strong ligand. Even if it is a weak ligand, doesn't matter. 4D and 5D, the metal ion will be having high splitting. Delta naught will be very high for 4D and 5D metal ions. 4D and 5D metal ions, delta naught will be very high. That is why what I mean to say is, doesn't matter whether it is a weak field or the strong field ligand. Whether it is a weak field or the strong field ligand, it will always be having delta naught greater than pairing energy. These things please keep it in mind. Geometry also important, tetrahedral complex. So whatever may be the kind of the ligand, doesn't matter, will be always be having a the high spin complex will be produced, because tetrahedral complex only you are having 4 ligands, whereas the octahedral complex you have 6 ligands. All those ideas you please keep it in mind. By having these ideas, we will slip over to the next part, that is splitting in the tetrahedral complex. I will not go details into the tetrahedral complex and the square planar complex. Idea is the same, that is splitting in tetrahedral complex. Just remember, it is reverse of splitting is reverse of octahedral complex. That is sufficient for us. For board exam, you may need to go through everything, how the electrons are, how the the ligands are placed. For the competitive, that is enough for us. We don't have the time to explain everything. Tetrahedral complex, what you are doing is you are keeping at the alternate corner of the tetrahedron. When you keep so, you will understand that the ligands which are in between the coordination axis will be, the d orbital which are there in between the coordination axis directly encounter the ligand, or it will be close to the ligand, whereas the d orbitals which are along the coordination axis, which will be much away from the ligand. That means dxy, dyz and dzx orbital will experience more repulsion than dz x square minus y square and dz square orbital. Very clear? So dxy, dyz and dzx orbital will be experiencing more repulsion compared to that of the dx square minus y square and dz square orbital. That means d orbital which is along the coordination axis will be away from the ligand field, because ligand is placed at the alternate corner of the tetrahedron. You have a 8 corner, right? Alternate corner you keep it, 4 ligands we have. So you will obviously observe that the dxy, dyz and dzx orbital will be closer to the ligand field, whereas these 2 orbital will be away from the ligand field. Since these are away from the ligand field, this is close to the ligand field, splitting in the tetrahedral complex will be ulta, that is reverse to that of our whatever we have observed in the octahedral complex. Octahedral complex, how it was the splitting? T2G below, EG up. Now EG is below, T2G is up. That is dxy, dyz, dzx will be here, dx square minus y square and dz square will be here. Very clear? So, or in other words, these orbitals are named as T2, as I already said. G should not be taken into the account for the tetrahedral complex, because tetrahedral complex doesn't have the center of symmetry. This is E orbital, this is T2 orbital. So, example we will take it NiCl4 2 minus if I take. For example, we will take it as Cu, ammonia, not required, Cu, not Cu ammonia. For instance, we will take, FeCN 4 times, now FeCN 4 times 2 minus, FeCN 4 times 2 minus, we will take it, this complex we will take. So otherwise we will go for something like, the Cu ethylene diamine, En twice, right? This also can be taken. Many things can be taken, doesn't matter. No, for example, the COBr 4 times 2 minus, COBr 4 times. So counter ion anyhow there, I am not interested in that much, right? We'll go, all are I am specifically telling, this is a tetrahedral complex. Why can't square planar? I will explain you, I will give you a hint how to predict directly you can predict whether it is a square planar or tetrahedral. These are all tetrahedral complex. We will come to that point later. Okay, so just try to understand how to find the CFSE for this. CFSE for nickel tetra, tetrachloronickel complex we will take care. So what is the coordinate, the charge of the nickel? Charge of the nickel is, complex is having -2 charge, we have 4Cl minus, charge on the nickel is +2. So nickel is a +2 state. Nickel tetracarbonyl also we will take it, NiCO 4 times. Right. So CFSE can we calculate quickly? Nickel +2. What is the system, student? The 3D system, 3D8, 4s2, 2 electrons had gone, 3d8 it is. It's a 3d8 system, 8 electrons you are having. Ligand is a weak field ligand, and alongside you don't have to worry about the strength of the ligand. Generally it will form the square, it will form a weak, high spin complex as far as the tetrahedral complex is considered. One we'll put 2, right, 3, 4, 5, right? We'll have to go up first, because why it has to be done so, because we'll be having a weak ligand there. 5, 6, 7 and 8, right? What is the electronic configuration? E2, sorry, not E2, E4, T24, E4, T24. How do you write the how do you calculate the CFSE? Each electron which is going to the lower orbital will be stabilized by -0.6 delta naught. Each electron which is going to the upper orbital will be destabilized by 0.4 delta naught. Clear? How many electrons are there? 4 into -0.6 delta naught plus 4 into +4 plus 0.4 delta naught, 4 into plus 0.4 delta naught, right? So that means it is -24 delta naught, 2.4 minus 2.4 delta naught plus 1.6 delta naught. That means how much it is? -0.8 delta naught, -0.8 delta naught. So what is the CFSE of NiCl4 2 minus complex? This is -0.8 delta naught. Clear? -0.8 delta naught. Same way we can take cobalt complex also, we can take it. So cobalt complex, how do you go ahead? COBr4 2 minus, COBr4 2 minus, cobalt is in +2 state, 27 it is. 27 means D7 system. D7 system, what will be done? D7 system, I'll rub off this. 1, 2, 3, 4, 5, 6 and 7. Clear? 6 and 7. That is E2. What is the electronic configuration of this particular complex? E4, T2, 3, E4, T2, 3. So how do you calculate? 4 into -0.6 delta naught plus 3 into 0.4 delta naught, right? So what is the answer? Minus 24, 2.4 delta naught plus 0.9 delta naught, right? Minus 2.4 plus 0.9 minus 2.4 delta naught plus not 0.9, I'm sorry, plus 1.2 delta naught. That means minus 1.2 delta naught is this. So which complex is stable, this or this? This is more stable than this. Why so? Because this has a CFSE minus 0.8 delta naught, this has a CFSE minus 1.2 delta naught. This is how you can predict the stability of the complex, or you can predict the CFSE of different complexes can be predicted by using this idea.